Hello everybody, welcome back to our channel. Now we are on question 2, okay? Quite straightforward question, okay? For A, okay, don't look at anything up there, okay? State the full electron configuration of an oxygen. Oh, easy, right? 1s2, 2s2, 2p4, yeah. Yeah, this oxygen, okay? And the number of unpaired electron in that atom, unpaired electron in oxygen is 2, okay? Okay, draw a Lewis structure of the ozone molecule. You need the textbook problem. You need to remember ozone. Okay, ozone. Okay, double bond, single bond. Actually, resonance structure, right? And then two, and then okay, two here, and then 6. Okay, textbook problem you have to remember. Okay, and deduce the formal charge. Remember the formal charge is the charge of each atom, assuming that all the bonds are equally shared by them. So for this one, yeah, 1, 2, 3, 4, 5, 6, 6 electron, right? Double bond 2 for it. Okay, so it's 0 formal charge. For this one, 1, 2, 3, 4, 5. Yeah, 1 less, so plus 1. So 1, 2, 3, 4, 5, 6, 7. Okay, minus 1. Remember, all the formal charge add together should be the overall charge. Okay, overall neutral, so should be 1 plus 1 and 1 negative 1. Predict the shape and the bond angle of the ozone molecule. Look at this one. It should be a V shape, right? V shape. So obviously it's a V shape. Okay, so it's V shape. And then about the bond angle, okay, including this lone pair, so it should be quite evenly distributed. It's a 180 degree, okay, but the lone pair is stronger, right? So this is less than 120 degree. So you need to have some guess, okay? So I would guess 117, 18, or 16, okay? Okay, state the hybridization state of the central oxygen atom in ozone. Relax, relax. Remember, single bond is a pi bond. Double bond is 1 sigma 1 pi, okay? Just relax, just write it down, then you can see it's hybridization, right? sp2. Don't think about it too hard, okay? Sometimes it's very straightforward. Okay, next one, okay? About a question C and D, okay? And then you look at the booklet, data booklet, okay, find out the ozone molecules bond length, okay? You remember it is a resonance structure. It is should be a mixture between single and double bond, right? In between them or something average, okay? So this one, data booklet said yes, 148 nanometer, and this one is 121, okay? Maybe take the simple average of them, okay? You guess, okay? Just guess, okay? Estimate. I have you 135 nanometer. And next one, explain that the dependency of the dissociation, breaking down of oxygen and ozone, okay, on the wavelength of UV radiation. So they absorb UV radiation and they break. And you have to think about which one is easier to break or harder to break. Okay, remember ozone, okay, 135, okay, longer bonding. So you say OV, longer, sorry, it should be PM, sorry, I forgot. Longer bonding, okay? So longer bonding will mean far away, okay, less energy is required to separate them, right? So less energy to dissociate. Yes. So it will absorb UV light of lower energy. Though remember, lower energy is a longer wavelength. So for OV, the UV lights that dissociated will have a longer wavelength, okay? But you have to say clearly is ozone's UV is longer wavelength than oxygen. Make sure comparison, okay? So that's it. Okay. See you for next question.